Hello everyone, I'm Oleg Guzev from Infotex. I will be speaking about the correlation of events. The type of correlation which will help us identify APT attacks in a simpler way. I will be showing just one particular case. What would be difficult to defend? And these attacks, they're multi-staged and distributed in time. If we do this analysis like it was, this attack may take from a few minutes to 6 months and even longer. So defining and detecting an APT attack by one sensor, sometimes it's not possible, only if you get lucky, or if SOC works well. And another condition is that the sensors are different and they employ different principles and they can give this information in different formats with different content. Number 3, unfortunately, there is just so-called information noise. All these sensors may have false positive reaction, and if there are dozens and dozens of sensors, such noise created by false positives is significant, and a small number of events of signaling the attack may just simply dilute there. There's no way to classify the incidents. Sometimes the SOC employees may just simply ignore some of such events, and there may be violating sensors, detectors, and anomaly detecting sensors. They say that something strange has happened, but they are not saying what tactics behind it. That's our source data. What's good with this correlation? And I would like to say that this slide does not explain anything yet about how to remove the noise. It just explains what this correlation algorithm does. On the left here there are sensors and a big number of events. It doesn't really matter what it works like. In the middle there is a correlation module and there is something going on in there. And on the right-hand side there is a possible attack. Possible attack includes the events that relate to it and that get there by some kind of algorithm, and all possible criticality levels, and they demonstrate how dangerous this attack may be. What's more important here is that there may be hundreds and thousands times less attacks than source events, and that's one of the main things, because it reduces the load on the monitoring, on the monitor, I would say. What did we want to get from this algorithm? We wanted this algorithm to support and operate with as many sensors as possible, not the compatibility-wise, but functionality-wise. And it doesn't really matter whether it uses statistics or signatures or anything else, just an algorithm, which is very easy to scale up or scale down. Ideally, it would be nice that the algorithm just does not simply notice it. It should correlate by time, by place, and by tactics. What's more important is that this algorithm works without any specific settings. So the operator would not think about the topology or toy with any IP addresses. So it should be a box solution, just out-of-the-box solution. It should generate the so possible kill chains to analyze and understand the reason behind it. And last but not the least, it should differ two concurrent but different attacks. This method does not replace other ones, but it adds more to them. A bit of a slide here, that's quite familiar. And since our companies have already used this MITRE matrix, we can use it. We can use this MITRE enterprise matrix with 14 tactics, and some of the tactics are more local, that are running on host. Some other tactics are network-related tactics, and the ones circled in blue, they are important for the algorithm because to a major extent they are network ones, and on the other hand they either get to the horizontal migration or data theft or some other serious aggravated results. And they are important for correlation and for the automatic launch of the algorithm. And one last text slide. The first definition is network group with a set of hosts. There may be just one host in the group and maybe 100. They are identified by IP address or some kind of ID. It doesn't really matter which one that would be for the algorithm. Possible kill chain, that's what we have at the output. Having events correlated by time, distributed by different tactics, and having proper time features. And here we have a few conditions to be met. The composition of the message from the sensor, it should include all these things: the time of the initiation, the place of the initiation. Desirably, there should be tactics, ID of the sensor, and the one final thing is everything specific for the sensor. How does it all work? Let's first talk about the correlation by place. Network groups, there are two of them, dynamic and static. Dynamic ones are created from zero and admin doesn't need to do anything. The static ones are created by admins, and that's how they live before the admin deletes them. Dynamic groups have a lifespan. Dynamic network groups will be animated shortly. On the screen you'll see how this simple, very simple case is explained. There are some stages missing from there, so the initial point was just to show how the dynamic network groups are formed. So imagine that we have our corporate network on the left with 3 hosts with A, B and C used as identifiers, IDs. IP addresses can stand for that, and right there we have a fraudster. We have initial access command server, and the Z stands for the one that will download the data. On the right-hand side, there are no network groups. I mean, initially. Then A and B sensors register some local events. For them, we have 2 network groups automatically created. One each, 1 hosts, 1 A, 1 B, and it's done automatically. Then the fraudster activates and starts the attack. We don't know what happened previously. They're trying to get access, exploiting one of the vulnerabilities, and a network session is initiated between the 2 servers. Host A had already been there, so it immediately increases the load. And there are 2 local events running. Maybe it's a part of an attack, maybe it's something independent. The host A events does not lead to the creation of network groups. It's added with index 1, and for host C we have a new network group created because there was an event running on it, so we have 3 network groups that you can see here on the slide. Host A starts interacting with the command server. It's registered by A sensor and it gets the Y in the list of the hosts. There's the horizontal shift. This horizontal shift leads to the network group starts inflating and growing, and group B remains the same because there are no events related to it. Yet there is again interaction with the command server, which does not change the network group 1 because there are all hosts used there. There is another horizontal shift. There should be a discovery, etc., etc., but that's not the point. And the C host gets to this group, and the events that we used to have in the network group C are added to the network group with index 1. Initial tree starts getting added the hosts to which we migrate. It's a false event. It does not create the change of the network group. It just adds the events there. And one final stage of the attack, data theft. Host Z is added there. Initially, there was nothing, as you may remember. The admin probably should have pointed out what were the alien IPs and what were ours. And this tree was created automatically. So the correlation by place means that every event relates to that network group and of which the host's IDs belong to the network group. And now correlation by time that runs in parallel to the one which correlates by place. There are plenty of details, but number one, each event has lifetime. Each event has the inception point. We analyzed the APT attacks conducted to understand how much time each tactics may take, maximum amount of time, and how these tactics interrelate. And if we know the inception of the event, the inception time of the event, we know after which time the lifespan of the event will be over. If the lifespan of the event is big, you need to store more events of such kind. And each possible attack also has a lifetime, also have lifespan, which matches exactly with the lifespan of the last event. This algorithm may detect the fraudsters backing up, so it requires us to do additional investigation, and some of the events may prove the tactics. Imagine that there is a horizontal shift occurring and two sensors have detected it, host sensor and network sensor, and the signature sensor says that that's an intrusion and the other one detects an anomaly. It could be collection, it could be horizontal shift, some other thing, and such events were very, very close by one another, and they relate to one host. And in this case, there can be a confirmation. The less precise event, tactic-wise, becomes more precise, and this is how you correlate events by time, also correlating them by place. Now I'm going to describe the correlation of events by tactics. It starts simply. Events are grouped by tactics because they are all marked, and each event is granted a weight. Imagine that a signature has worked and it has pointed to an execution. It gives the weight 1 to it. It's the most valid event. Or some abnormal sensor informed us about an anomaly occurring, which points to 4 different tactics. If we divide 1 by 4, it equals 0.25, and that's the weight. And these weights are used to calculate the metrics. On this slide, at the same time as I speak, I was trying to show the example of this algorithm in progress. I cannot, of course, show the real data examples because it will contain quite a lot of real data related to our network. I've taken this example from the internet. I diluted it with the events. I added some other sensors there, and I'm showing here, not completely because there is a lot of text, but it briefly explains how this algorithm was used here for this particular attack. The algorithm reveals this information for each particular tactics by weights, and how many events are there, how many events which are given weight 1, how many returns did the fraudster commit, what's the average weight, how many hosts were used in these possible attacks, what tactics have been used, what was the time of the inception, what was the time of the end. And that's what we can have here. There are 14 altogether, and in the end we will generate you the criticality level. It's 5 here. It means that there are 5 tactics in this particular attack with weight 1. It's not the only criticality level. There's also the one considering the senior tactics. It could be false, it could be something else. Probably that's the correlation. So everything which I said is not going to work if we don't get rid of the noise, because you won't be able to go through all those printouts, and the operator is very likely to ignore it. What are the ways to get rid of the false positives? Well, we can of course use it in different parts of algorithms. We can filter these events, and a very simple filtration rule is for each particular event we single out a set of unique fields, see how very frequently it springs up, and we just nip these events in the bud without using correlation. ML can also be applied here, which we didn't use because such events were simple. But ML could possibly be used here, and also inside this algorithm we can aggregate the events. Equal events can be counted by counter, and we should not store them all. It will help us save the resources, not getting rid of them. And what we do after the correlation algorithm is the filtration of the attacks. For example, what kind of criteria are used here? We select the attacks that have more than 2 internal hosts. So, for example, there is some horizontal shift occurring, and the criticality level exceeds 2, so more than 2 tactics should be represented here. And initial access is there, that's the senior tactics. One of the first tests we conducted was taking 300,000 events, out of which there were 19 possible attacks, and the monitoring operator can easily manually look through these 19. It's not a lot. We also tried at that particular phase to use ML, also convolutional auto-coding. We thought it would be useful because each attack is a set of events, and each event could be a vector, and we turn the attack into matrix, and we put it into the convolutional autocoder, which detects a norm and anomaly, but the attacks are growing in size, so they'll be getting bigger and bigger. We decided therefore not to use it, but altogether it will give you a very adequate result which can be used to get additional high-level signal to detect APT attacks. Thank you very much. Do you have any questions? Thank you for your presentation. What are the means of correlation that you use? Correlation means by time. I'm talking about the source of the attack and target. The source is the host of the fraudster by time, also by tactic. And if we're talking about the correlation means, it's just a code which pulls out data from the event and correlates it, if I understand that question right. Yes, you did. So basically it's the rule. No ML is used there. Thank you for your presentation. Just a couple of questions I have. We filter the noise. So what if we just filter them in a wrong way and we miss the attack? Are there any more precise ways to filter it? Well, expert experience is required here. So there is a danger of using ML because in different networks the situation may be different and we may skip something. So expert experience is needed here. So we're talking about APT attack, which may last for a long time. What if we deploy this system after our system has already been attacked? Will we be missing the attacks? Consider them as noise. It really all depends whether they're going to feed retro data there to the algorithm. But if this algorithm starts working from now, it will be catching the events from this moment on. Okay, thank you very much. Could you pass the mic to that speaker? Thank you very much for your presentation. I have a question regarding this time correlation. You were showing this comparison. You were showing the correlation inside the attacks between different tactics. And I have a question. What would be the advantage of using this correlation mechanism in this particular case? If you also have a chance to use any ERP system with automation without using the correlation mechanism. And as I see it, we can make it much easier for the correlation means. I just would like to understand the advantages of this particular approach. I think the advantage of this particular approach is simplicity and predictability, because this inflow of events in the network is a very complicated event. So the simplicity of the algorithm is key here. I understand, but I understand the advantages in terms of this correlation engine. That's the point of my question. This algorithm was developed to address those tasks which we were facing. As for the advantages, let's maybe discuss it later on, what we can compare it with. But here we don't have any claims about this universal approach or new solution. We were just trying to tackle the tasks we had to tackle. Thank you very much.